All right, good morning, everybody. This is April the 9th. This is College Algebra. Just a couple of quick announcements here. WebAssign is, your next WebAssign homework is due on the April the 15th, so that's this Sunday. It's section 6.4 and 6.5. And then section 6.6, there's actually two homework sets out of section 6.6, and those will be due April 24th. And we're almost done with WebAssign homework. There's like five assignments left for the semester, so it's going pretty quick. Exam 3, the review is posted. I posted it this morning, and I've been told by a reliable source that it's very intimidating when you go and look at it. Just remember so it's a lengthy review. There's lots of problems on there. Remember, the review is a lot longer than your actual test, but there's lots of good practice problems on there. And that's I've posted it now a good 10 days ahead of where the Exam 3 window opens, so you've got lots of time to practice and lots of time to ask me questions about that review. Office hours, let's see, so online office hours, I've got Sunday and Tuesday, 8:30 to 9:30. Oh, and I don't know why I didn't list but then also Tuesday, Wednesday, and Thursday mornings from 11 to noon. I'm almost always online those hours, those 5 hours during the week. And like last night, I was online 8:30 to 9:30, and I was online completely by myself. No one came by to talk to me at all. So, you've got good opportunities online to come by my WebEx room and ask questions, so try to take advantage of those online hours. On-campus hours, so let's start thinking about that a little bit now. Not this week, but the following week, April 18th and 19th, I will be on campus for office hours, probably 4 to 6 and 9:30 to 11:30 like I've got listed there. So take advantage of those hours and come by and see me and ask some questions face-to-face in person. That would be a good opportunity to get some last things cleaned up before you take Exam 3. All right, today we will be talking about logarithm properties out of section 6.5. We've got really 4 properties besides what we've already talked about with logarithms that we want to write down and look at. And then we will start gradually using those properties as we look at different types of equations to solve, and also some word problems as well, with compound interest in particular. So the way I'm looking at this is I will do solving exponential equations part 1 today, and then on Wednesday I'll look at exponential equations part 2, and then we will start in on logarithm equations and get pretty far into log equations on Wednesday also. All right, so logarithms. Let's talk about logarithms here. This has been a big topic for us the last couple of lectures. And so let's write a few things down, kind of get some things all together here, and then we're going to look at properties of logarithms. Don't forget, first of all, that when you have an expression that's in logarithm form, or an equation that's in logarithm form, y equals logarithm base b of x, that is equivalent to b to the y equals x. And remember, the first form is called the log form of the expression, and the second form is called the exponential form. And certainly you need to be able to go back and forth between those two forms. Lots of times an expression is much easier to deal with in the other form than in the form that it's currently written in, so you need to be able to go back and forth between those. Also, don't forget that logarithm base b of x is equal to an exponent. Right? Logarithms are always equal to exponents. And what is just exponent is what I'll say there. And remember what the exponent is. It's the power. So you ought to be able to always say a logarithm to yourself as far as what it represents. And it's the power you raise b to get x. Right, so never forget that it's the power you raise b to get x. And then just 1 or 2 other things here to write down. Don't forget that we have that log x is an abbreviation for log base 10 of x, right? And that's the common log. That's the name for that type of logarithm. So when you don't see a base written down, it's understood to be base 10. And when you see ln x, that's also a logarithm, remember, that's just notation. And that's a representation for log base e of x. And this is called the natural log. And don't forget, obviously, that e is approximately equal to 2.718, right? That e, that's the value of e. And these come up often enough that you need to be able to write these down. Don't forget that log of 10 is equal to 1, and the natural log of e is equal to 1, right? That's log base 10 of 10 and log base e of e, that those are both equal to 1, and that log of 1 is equal to 0, and the natural log of 1 is equal to 0. Don't forget those little facts also. All right, so now let's talk about our calculators for a minute. Hold on, let me get my calculator here real quick. You know, if you're going to try to use calculators with logarithms to evaluate an expression, so using calculators, first of all, you know, don't forget that logarithms like this, log base 10 of 100, you don't need a calculator for that. That's equal to 2. Because that's the power you raise 10 to get 100, so you don't need a calculator to evaluate that. Something like log base 4 of 64. You don't need a calculator because that's the power you raise 4 to get 64. That's 3. Don't need a calculator there. But then when you start talking about things like this, let's say the log of 500, let's log base 10 of 500, and all of a sudden you do need a calculator if you want to get a decimal value for that, because that's the power you raise 10 to get 500, and that's not an exact power, right? And so there, on your calculator there, you're going to enter, and that's an easy one to enter because all you're going to do is enter the log key and then 500, and then close the parentheses with a right parenthesis, right? And when you do that, let's see, so on my calculator, log of 100, or I'm sorry, log of 500, I get about 2 point, and let's see, so I get log of 500 to be approximately 2.69, we'll say to 3 decimal places, right? So to 3 decimal places, 2.699. All right, I just rounded the 3rd decimal place there. And so remember what that 2.699 represents, because this is logarithm base 10. This is the power you raise 10 to get 500. So presumably on your calculator, you could take 10 and raise it to the 2.699 power. And you'd get close to 500. You wouldn't get actually, you're going to get a little bit bigger than 500 here because I rounded up. Let's see. I get 500.03 about. And that makes sense. I should get a little bit bigger than 500 because I rounded that decimal up. So that's a problem you would need a calculator for, right? So you log of 500. The natural log of, let's say, 1,000. So this is the power you raise e to get 1,000. And again, this is something you wouldn't know off the top of your head. You'd need a calculator. So on your calculator, you would enter the natural log key, and then 1,000, and then again the right parenthesis. So you'd have natural log of 1,000, close off those parentheses, and I get about 6.908. So on my calculator, I get a natural log of 1,000 to be approximately 6.908. Now remember, what that 6.908 represents is the power you would raise e to get 1,000. So it should be the case that if you take e and raise it to the 6.908 power, you should get about 1,000. Now again, I rounded this up, so I'm going to get a little bit more than 1,000 when I do that. But when I do this on my calculator, I get 1,000.24. And it makes sense that your answer would be just a little bit too big here because I rounded that decimal up. Okay, so, and these are all things we've done before in lectures. So if you were watching through the lectures last week, we've done this kind of problem before. But when you enter something, or when you have something like this, let's say log base 5 of 100, well, this is a problem when you have log base 5 of 100 because your calculator only speaks in two bases. The calculator only speaks in base 10 and base e. So in the calculator, there's not really a way to enter this directly. So your calculator only speaks, and I'll put speaks in quotes there because it's not really talking, right? But calculator only speaks in base 10 and base e. So the question is, how do you evaluate something like this on your calculator? And here is where we use, and we're not going to prove this, but we're going to use what we call the change of base formula. The change of base formula. The change of base formula is a way of taking a logarithm in one base and changing it to a logarithm in a different base. And the change of base formula goes like this, that, logarithm base b of x, so that's a base b logarithm, is equal to log base a of x divided by log base a of b. This is a way of taking a base b logarithm, whatever the base happens to be, and changing it into a base a logarithm. It's a way of taking a logarithm and actually changing its base. So log base 5 of 100, using the change of base formula, we could write it as a log base 10 by writing it this way, that this is log of 100 divided by log of 5. And notice I changed it to a base 10 logarithm here, so I'm using the common logarithm. I could have used the natural logarithm also. The idea here is you want to try to use your calculator, so you're going to change to either base 10 or base e. It doesn't make any difference which one, by the way. So I could have also written this as the natural log of 100 divided by the natural log of 5. You're going to get the exact same value either way. All right, so on your calculator, what would you do here? By the way, log of 100, as it turns out, is one that you know. So that's nice. That's just 2, because that's the power you raise 10 to get 100. And so this is 2 divided by log of 5. And so on your calculator, let me erase that there. On your calculator, you would enter, so on the calculator, you would enter 2 divided by, and then log of 5, like this. That's the way it would be entered on your calculator. So 2 divided by log of 5, close off the parentheses, and I get about 2.861. 2.861. Now, log base 5 of 100 in words is the power you raise 5 to get 100. And so you could check that on your calculator. You could check this by taking 5 and raising it to the 2.861 power. And you better get pretty close to 100 when you do that. 5 raised to the 2.861 power is about 99.94. And that makes sense that this would be a little bit less than 100 because I rounded the decimal, the 2.861, down a little bit. And so 99.94, that would make sense. And so that would certainly means you're good there. All right, so let's look at another problem like this. So all we're doing is practicing using the change of base formula to take a logarithm that's not in base 10 or base e and use it to be able to use that formula to be able to use your calculator to evaluate things that are not base 10 or base e logarithms. So let's say we have log base 8 of 1,000. Let's not use a power of 10 there. Let's say log base 8 of 197. Just something crazy. All right. So log base 8 of 197. You cannot use your calculator directly to evaluate that. So on your calculator, you'd use the change of base formula. So use change of base. And so using the change of base, let's use the natural log in this case. This would be the natural log of 197 divided by the natural log of 8. That's all you have to do. And notice the two numbers are kind of written, the way you write a logarithm, it is kind of in the right order, because the 197 is kind of written above the 8 in the original logarithm. And notice that's the way you write it in the change of base formula. So it's fairly easy to remember it. So on your calculator, you would enter natural log of 197, close off those parentheses like that, divided by, and then natural log of 8, and make sure that you close off those parentheses. So that's the way you would enter that on your calculator. So the natural log of 197, close the parenthesis, divided by natural log of 8, close the parentheses. I hit enter at the end, and I get about 2.541. 2.541 as my value there. And so you could check that. You could take 8 and you could raise it to the 2.541 power. And you better get pretty close to 197. In this case, I rounded this decimal up. The 2.541 is rounded up from what I had on my calculator. I'm just rounding to 3 decimal places, by the way. So, and I just picked 3 decimal places just because it gave us a convenient number of decimal places to use. There was not really any inherent reason why I did that. So you have 8 raised to the 2.541 power, and I get 197.129, blah, 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 like that, and which makes sense. A little bit too big. It's a little bit bigger than 197. All right, and let's finish this one last problem. Let's say I have logarithm base 2 of 384. Logarithm base 2 of 384. So this is the power you'd raise 2 to get 384. You could certainly go through and kind of get an estimate on this on your own. You know, 2 to the 6th power is 64. 2 to the 7th power, so that's too small. 2 to the 7th power is 128, too small still. 2 to the 8th power is 256, still too small. 2 to the 9th power is 512. Notice that's too big. So this is too small right here. This is too big right here. And notice that tells us that the answer better be some number between 8 and 9. Right? All right, so on my calculator, what would I do? I would rewrite this, first of all, as, let's say, a base 10 logarithm. So this would be base, or log, common logarithm, log of 384 divided by log of 2. That's using the change of base formula. And so on my calculator, I would write this as, or enter this as log of 384. Close off, make sure you close off those parentheses, divided by log of 2, like that. So log of 384, close the parenthesis, divided by log of 2. close parenthesis, and I get about, and this makes sense based on what we just talked about, 8.585, rounding to 3 decimal places. And notice I got an answer between 8 and 9, right? It makes sense. 2 to the 8th power was 256, was too small, was smaller than 384. 2 to the 9th power was 512, which was too big. 512 is bigger than 384. So there must be some decimal between 8 and 9 where I can take 2 and raise it to that power and get 384. And it's approximately 8.585. Okay. So that was the change of base formula. All right. So now our next step, properties of logarithms, other properties of logarithms. We'll say that. Other properties of logs. And these next properties are very important if you want to solve equations that involve logarithms, which we're going to be doing. They're very important for calculus students. For those of you who are either with me live, I know at least 1 or 2 of you that are with me live today are business majors, and you're going to go on and you're going to take elements of calculus and finite math. In elements of calculus, anybody who's taking a calculus class, properties of logarithms are very important when you're dealing with logarithms. Calculus students use these properties constantly. I could prove all these properties using properties of logarithms, properties of exponents. Remember, logarithms and exponents are really the same thing. I'm not going to go through and prove these. I'm just going to state these rules. And so the first property or the first rule is called the power rule. And I just call these either laws or rules. So the power rule for logarithms, it goes like this. If you have logarithm base b of x raised to the r power, like that. So if the x is raised to the r power, that you can rewrite this as r times log base b of x, like that. That you can literally bring that exponent that's on the x there and bring it down in front of the logarithm, and that these are the same thing. Now this rule makes sense because of this rule right here. The rule for exponents. It makes sense that you multiply. Notice that's what you end up with here at the end of this rule is a multiplication problem. And it makes sense because of this rule, that if you have x to the a raised to the b, what do you do with the exponents? You multiply them, x to the a times b. It's really the same version. It's a different version of that rule. So the power rule, as an example here, states that if you have log, it doesn't matter what base it is. So notice that's why I wrote base b. That means this rule is true for any base. That if you have log of, let's say, x raised to the 5th power like that, that using the power rule, you can literally take that 5 and write it as a factor in front of the logarithm. That these are actually the same expression. That log of x to the 5th is really 5 times log of x. And natural log of z to the 4th power, like that, that since there's an exponent on the z there, that I can bring that exponent and write it as a factor in front of the logarithm. That these are really the same thing using the power rule. Notice that gives you, by the way, a way of doing a problem that we've talked about earlier in this our little unit on logarithms. We were looking at problems during the semester like this, that like if you had logarithm base 2 of 2 to the 5th power, notice that you could use this power rule and bring that 5 down in front as a factor. And then that leaves you with log base 2 of 2. And remember, log base 2 of 2 is the power you raise 2 to get to. So that's equal to 1. So you have 5 times 1, because that's what logarithm base 2 of 2 is equal to, is 1. It's the power you raise 2 to get to, so that's why it's 1. And so that just gives you 5. And so that's another way of we did this a different way earlier. Let me rewrite that real quick here. Earlier in the chapter, we did that problem a different way, but you could use this power rule to evaluate log base 2 of 2 to the 5th and get 5 as the answer. Okay, so just kind of wanted to point that out there. All right, so notice that, continuing on with some examples here of the power rule, if you have log base 3 of the square root of z, log base 3 of the square root of z, that the square root of z, remember, is really a power. We've talked about this now several times again, but remember, square root and 1/2 power mean the same thing. So square root of z and z to the 1/2 power are really the same. And then you can bring that 1/2 power down in front using the property, this power rule for logarithms. So this is 1/2 times log base 3 of z, like that. Right, and so that would be a situation where you would see the power rule come up. All right, so the power rule is a big one. We will definitely be using the power rule again today, so that's going to come up again for us. Okay, so the next rule is called the product rule. So here's the power rule. The product rule has to do with how you take a logarithm of a multiplication problem. So if you have logarithm base b of x times y, using this rule, this is logarithm base b of x plus logarithm base b of y. That you can take the log of a multiplication problem and you can rewrite it as the sum of 2 logarithms, like that. It's called the product rule, and this makes sense because of the rule for exponents and how we take a multiplication problem with exponents, x to the a times x to the b, and what do we do with those exponents when we multiply bases like that? We add the exponents, right? And so notice this is connecting multiplication and addition. And so this rule of logarithms, the product rule, is really just a way of restating that exponent rule that you already knew. All right, so this rule applies in a situation like this then. So if you have log of, let's say, 5x, right, log of 5x, using this product rule, we could rewrite this as log of 5 plus log of x, like that. That's what this rule is stating that we can do. That if you have a log of a multiplication problem, it doesn't matter what base logarithm you've got, that you can always rewrite it as the sum of 2 logarithms of each of the factors that you've got. So if we have the natural log of, let's say, x times a plus b, something like that, the natural log of x times a plus b, let me put big brackets here, that way it kind of looks a little bit better maybe. So that's a log of a multiplication problem, and so that would be the natural log of x, the natural log of the first factor, plus the natural log of the second factor. The second factor here is a plus b, so that'd be the natural log of a plus b. All right, so those are some brief examples of the product rule right there. And actually, let me write a little bit. Let me write another example here. Let's say we have log of 100x squared. So there's a little bit more going on in this problem. First of all, it's a multiplication problem. So this would be, using the product rule for logarithms, this would be the log of 100 plus the log of x squared. It's the log of a multiplication problem, so it's the log of the first factor plus the log of the second factor. Now, as it turns out in this problem, the log of 100 is something you can evaluate because that's the power you raise 10 to get 100, and so that would be 2. If you can evaluate it like that, you always do that. Don't leave it as the log of 100. And so that would be 2 plus, and then the log of x squared. That's a power rule problem, and so you can bring that 2 down in front, and you get 2 times the log of x, like that. All right, so that's an example, a brief example of the product rule. So now let's go on to the quotient rule next. And so this is the quotient rule for logarithms. Let's see. Okay. So this is the quotient rule. And so the quotient rule has to do with how you take the log of a quotient. In other words, the log of a fraction. Right? And the quotient rule says that this, the log of x divided by y, the log of x over y, would be the log of x minus the log of y. It's the log of the numerator minus the log of the denominator. And this rule makes sense. You know, all the rules have a kind of a corresponding rule in exponents. This makes sense because how do you take in a exponent problem where you have division, like x to the a divided by x to the b, what do you do with the exponents in that situation? You subtract them, right? And so what is this linking? It's linking how you divide two expressions with exponents to subtraction like this. It's exactly what this rule is doing, right? It's connecting that division process with subtracting the exponents. All right, so this rule is an example here. If we had log base 3, we'll use, it doesn't matter what logarithm we have, logarithm base 3 of 3x over z. Log base 3 of 3x over z. That's the log of a fraction. It's the log of a division problem. So this would be a quotient rule problem. And this would be the log of the numerator minus the log of the denominator. Well, it's always the log of the numerator minus the log of the denominator. And now notice the first term is a log of a multiplication problem. So this is the log of the first factor plus the log of the second factor. And this would be minus the log base 3 of z here. And so that's the product rule right there. And then log base 3 of 3, the very first term, that's the power you raise 3 to get 3. And so that's 1 because the 3 to the first power is 3. And so then you have 1 plus logarithm base 3 of x minus logarithm base 3 of z. All right, so what we are going to do here is kind of look at some problems, more big picture kind of problems, where we're looking at a lot of these rules combined. And the first way we're going to look at this is we're going to talk about expanding logarithms, which is kind of what we've been doing anyway. So, and that's the word that I will use in directions. I'll say expand the following logarithms. So when I'm expanding it with logarithms, what I'm doing here is I am starting with one logarithm. So let's say we have log base 4 of, let's say I have x cubed over y to the 5th, like that. Log base 4 of x cubed over y to the 5th. When I'm expanding a logarithm, what I'm doing is I'm starting with one logarithm and I try to expand it out and until I can't use these rules anymore, basically. Until I can't use the quotient rule, the power rule, or the product rule anymore in the problem. You just have to be careful about the order that you use these rules in. Now I've got powers here, but I can't use the power rule yet because this is not the log of something raised to a power. What I do have is a log of a fraction. And so this is log base 4 of x cubed minus log base 4 of y to the 5th, right? Because I had the log of a fraction. I had a quotient rule there. And then both of those are now logs of powers. And so I can bring those powers down in front. Let me clean up the way I wrote that real quick. I can bring those powers down in front as factors. And so this is 3 times logarithm base 4 of x minus 5 times logarithm base 4 of y, like that, right? And I've expanded that original logarithm, right? What you're going to do is you're going to start with one logarithm, and then you're going to end up with all these different log terms in the expression. All right, so that's our first example of expanding a logarithm there, though I've really been doing that with some of the other rules up above a second ago. All right, so let's look at another example here. Let's say I have log base 8 of x to the 5th times x plus y divided by the square root of z. Yuck. Right. And this is about as complicated as I'm going to get with expanding logarithms is a problem like this one. First of all, do you have the log of something raised to a power? Is the whole expression raised to a power? No, it's not. By the way, one other thing before I do anything else, when you have a radical in there, rewrite the radical before you do anything. Rewrite the radical as an exponent when you're simplifying using these rules. So don't leave it as the square root of z. Write it as z to the 1/2. If it was, remember, if it was a cube root of z, it would be z to the 1/3. All right. So now, is the entire expression raised to a power? No. You got some powers inside there, but you don't have the entire expression raised to a power. Instead, here what you have is you have a log of a fraction. And so you take the log of the numerator minus the log of the denominator. Like that. So that's the quotient rule right there. Right? So I use the quotient rule. And then in the next step, this expression here is the product rule, because it's the log of a multiplication problem. And so that would be log base 8 of x to the 5th plus log base 8 of x plus y. And now I'm going to be able to do this last term also, but let me just write this one down like that, and then I'm going to use the power rule next, right? This is now a power rule in this step, so this is power rule right here. This one is also the power rule. And then that middle term, let me point out that there is no sum rule, no sum or difference rule. Those don't exist for logarithms. And so the log base 8 of x plus y is just going to be the log base 8 of x plus y. There's nothing you can do to simplify that and rewrite it. No sum or difference rule. So be really careful about that. Right? And that makes sense with exponents if you think about it. Let me write real far down here. X cubed plus x squared. There is no rule of exponents that says you can add two exponent expressions together. This is not x to the 5th, right? You can't add unlike terms like that. And it's the same with logarithms. The log of an addition or subtraction problem, you can't mess with it. Now this first term would be 5 log base 8 of x. And the last term would be 1/2 times log base 8 of z. And so what I've done is I've gone ahead and I've expanded that logarithm, right? This was remember what the original problem was here. The original problem, or the original expression, was that logarithm expression right there. And what have I done? I've expanded it so that it looks like this one right here. Notice that each individual logarithm, even though there's more logarithms, each individual one is the log of a much simpler expression. That's really what you're trying to do when you expand a logarithm. All right, so that's expanding. So now if we go the opposite direction, so going the opposite direction, and you'll see what I'm talking about as we look through a problem or two here. What I'm going to do here is I'm going to call this contract the logarithm. That's the rule. That's the word I'm going to use in directions for this kind of problem. So this is what I'm talking about here. So for example, contract this logarithm expression right here, log base 5 of x plus log base 5 of, let's say, 4. So notice what you've got here is you've got several logarithms, in this case added together. And so to contract, you have to think about what rule you would use to combine these two logarithms into one logarithm. Since this is addition, this is going to be a product rule problem, because that's what the product rule is. And so this would be logarithm base 5 of x times 4. And so you've contracted it. When I say contract, you've taken several logarithms and you're combining them together as one logarithm like that. Now, usually you wouldn't write it as x times 4. You'd usually write this as log base 5 of 4x. Right? That's the contracted expression. I would certainly not penalize if you didn't write it that way, but I would want to make sure that you showed me that it was a product rule to contract it. All right, so let's contract this one. Let's say we have log base 10, so let's say the common logarithm of x plus 5 minus log of x, like that. All right, so to contract these two, first of all, you have to decide what rule you're using to combine the logarithms. And because this is subtraction, you would use the quotient rule to contract these. And so to contract these, this would be log of x plus 5 over x. And it would be the log of x plus 5 over x. Not, and this is a very common mistake, this is not log of x plus 5 divided by log of x. That is not the quotient rule. Right? The quotient rule says that the first expression is the numerator, the second expression is the denominator. It's not that you've got a logarithm in both the numerator and the denominator. So you have to be really careful about how you write this. All right, contract. In this case, let's say we have 3 natural log of x plus 5 natural log of y minus 2 natural log of z. Right, so you have all these logarithms. They're all natural logs, so they're all the same base. And we're going to contract these. So the first thing to do here when you're contracting is first, excuse me, always use power rule first in a contraction problem, if you can. So always use the power rule if possible. So the power rule, right, in this case is because I have this 3 in front of that logarithm as a factor, this 5 in front is a factor, and this 2 in front is a factor, right? Each one of those is a power because those are factors in front of the logarithm. And so when I contract, I would be bringing those up as exponents. And so this is natural log of x cubed plus the natural log of y to the 5th minus the natural log of z squared, right? Always bring those exponents up on the expression there. And then go from left to right next. So how am I going to combine these first two logarithms here? Well, since it's an addition problem, that would be the product rule. and that's because it's an addition problem, right? And so that would be the natural log of x cubed times y to the fifth, right? That's combining those first two. That's contracting those first two. Minus the natural log of z squared there. And then because this is a subtraction problem, I'd combine these two using the quotient rule. And so using the quotient rule, we would rewrite this as the natural log of the numerator over the denominator. So this last denominator would be z squared. And I usually put brackets or parentheses around an expression like that. And so now I've combined it and I've contracted, right? These are all contraction problems where you're starting with several logarithms and you're trying to combine them into one logarithm here. All right, let's see. So I want to do one more example like that where I contract. So let's say I have 1/3 natural log of a plus b minus 4 natural log of a. Like that. And let's make this even more difficult. Let's say plus 1/2 natural log of b. So this is really yucky problem here, and probably harder than a problem you would see on a test overall. All right, so now remember what I told you to do on this last problem. The first thing to do when you're contracting is to identify any powers. So those are all these factors sitting in front of each logarithm. Those are actually powers, right? And so using the power rule, we're going to bring those up as powers. So this is the natural log of a plus b to the 1/3 power minus the natural log of a to the 4th power. And then plus the natural log of b to the 1/2 power. Now, usually when you have fractions as exponents like that, when you're going back like this, you typically would write those as radicals when you're going back. So this a plus b to the 1/3 is really the cube root of a plus b. You wouldn't have to do that, but that's typical. And the a to the 4th, there's nothing to do there. And then the natural log of b to the 1/2 would be the square root of b, like that. Whoops. All right, so now how am I going to combine these first two logarithms here? Because it's subtraction, that would be the quotient rule. And so this is the natural log of the cube root of a plus b divided by a to the 4th, like that, plus the natural log of the square root of b. And then those two logarithms get combined using the power rule. Clearly not the power rule, the product rule. There you go, that's better. Because it's an addition problem. And so this would be the natural log of, and how are we going to write this? Well, this is the cube root of a plus b over a to the 4th times the square root of b. You know, and quite frankly, if you just left it like that, I would be fine with that. You might see it written like this: the cube root of a plus b times the square root of b in the numerator, all divided by a to the 4th. But I would take either one of those two. Either one of those, I'd be overjoyed, actually, if you would get to that point and write it out like that. That would be awesome. All right, so the main idea here with these last three rules is you should be prepared to either expand or contract. Right, expand means you're starting with one logarithm. So let's see, expand means you're starting with one logarithm, right, and you end up with several logs. Yeah, who knows? Addition, subtraction, whatever. Right, contract means you're starting with several logs let's say a log, you have log base b of something plus log base b of something, blah, blah, blah. And what are you going to end up with? You're going to end up with just one logarithm here at the end. Right, and so that's a contraction problem. And you should be prepared for either direction, certainly on the test. And I am not going to, I tend to not go crazy with this on a test, just so you know. But you got plenty of examples on your review for this. So you have lots of practice problems, and there's textbook problems on this that are good, really good review problems that you can also look at. This book has a lot of good practice problems on logarithms. So, so lots of good things that you can be looking at as far as practicing. All right. So that's it for properties of logarithms. And so now what we're doing, let's see, so we've got about 15 or so, 20 minutes left for class today. What we're going to do now is we're going to move on to solving equations with exponential expressions log expressions, and then finally, applications, compound interest problems, where equations come into play. All right, so that's what we want to move on to for the rest of this unit on exponential and logarithm functions. So what we're going to do here is we're going to move on to, first of all, exponential equations. And I'm going to title this Part 1. And these are equations that can be solved without logarithms. Equations that can be solved without using logs. And then on Wednesday, we will look at exponential equations Part 2, and we'll look at exponential equations where you absolutely have to use logarithms in order to be able to solve the equation. All right, so first of all, an exponential equation, remember, is an equation that has an exponential expression in it. And so if we look at, for example, this equation right here, let's say we have 2 to the 3x equals 8, like that. 2 to the 3x equals 8. Something relatively simple to start off with. This is a typical example of a relatively simple exponential equation, and this is what fits into this first category, these Part 1 problems right here. And what happens is this. I want you to think about this equation. Notice that 8 happens to be a number that is a power of 2. That I could take 8 and I could rewrite it as 2 to the 3rd power. And so look at this equation that I've got now. 2 to the 3x equals 2 to the 3rd power. And we're looking for x values that make this equation true. And as it turned out, notice that the bases on both sides of this equation were the same. And we can actually use this idea of exponents, that if you've got b to the x power equals b to the y power, notice that the bases are the same on both cases, on both sides there, that the only way that can be true, because of the way exponential functions work, that they're one-to-one functions, it's got to be true that the exponents have to be the same also. That's the only way that that could be true. If you have b to the x equals b to the y, is that x has to be equal to y, that the exponents have to be equal. That's a nice little property of exponential expressions, and you can use that sometimes with exponential equations to solve them. Notice that's what I've got in this step here. I've got the bases to be the same. And so the only way that can be true is if the exponents are the same. That 3x has got to be equal to 3. And now you've got a super simple equation to solve. You get x equals 1, and there's my solution to the equation. Right? I get 1 as the solution. It's very easy. And by the way, there's no way you can get an extraneous solution in this kind of problem. And so that's the nice thing, is if you've done everything correctly, you should certainly always check your work. But there's no way you can get an extraneous solution when you're using this property right here. Now, if other things come into play, yeah, that could happen. But just using this property, there's no way you can get an extraneous solution. All right, so let's say we have 5 to the 3x minus 4 power equals, and let's say we have 125. 5 to the 3x minus 4 power equals 125. Well, that exponential equation, if you're going to solve that, you could use the idea here that 125 is really 5 to the third power. It happens to be a power of 5. And I made it up that way so that it turned out to work out like that, right? So all the problems we're going to look at right now are going to have this property here. So I can use our property that I've got up here in this equation, right? Because what have I got? I've got that the bases are the same on both sides of the equation. So the only way that could be true is if the exponents are the same. That 3x minus 4 has to be equal to 3. And now you have an easy equation to solve. You just add 4 and divide by 3, and you get x is 7/3. And there's the solution to that equation, is 7/3. Right? Again, you could check 7/3, and you'd find that that would make it a true statement like that. So this idea of the bases being the same is the kind of equation we're talking about right here. These are these part 1 exponential equations that we're talking about. Now I'm going to look at several like this, so because they can get a little bit tricky here as we go through this. So let's say that I have 6 to the 5x minus 3 equals, let's say, 36. All right, we'll look at one more problem like that directly here. So 6 to the 5x minus 3 equals 36. Excuse me. The 36 happens to be 6 raised to a power. Right? It's 6 to the second power. And what do we get here? That the bases, sure enough, are the same here, and we can use our property that we were talking about on the last screen. That if you have b to the x, if b to the x is equal to b to the y, if the bases are the same on both sides, then it has to be true that the exponents have to be the same also. That's the only way that could be a true statement. So 6 to the 5x minus 3 equals 6 squared. The only way this could be true is if the 5x minus 3 was equal to 2. And so what happens there, you get an easy equation to solve now. You get 5x equals 5, x is 1. And so very quickly you get a solution to this equation, right? This is the key right here, is making sure that the equation is written so that the bases are the same on both sides, like that. That's the key. All right, let's say we have 8 to the 5x power is equal to 4 to the 3x minus 1 power. Now this one's not quite as obvious, definitely not. But what's going on here is that the 8 and the 4, so 8 and 4 are both powers of 2. Right? 8 and 4 are both powers of 2. So you could take advantage of that. Right? You could take the 8 and you could write it as 2 to the third power. Now that's still, it was 8 to the 5x, so now it's 2 to the third to the 5x. 4 is 2 to the second power. This is 2 to the second to the 3x minus 1, like that. Now it's not quite ready to go yet, but that's a good start to write the equation like that. All right, so now the next thing I could do here is, remember what the rule of exponents is you multiply exponents in a case like this. On both sides of this equation, you multiply exponents. That's the rule of exponents here. So that would be 2 to the 15x equals 2. Now this is a place you got to be careful on the right side. This is 2 times 3x minus 1. So it's actually the distributive property when you're multiplying exponents there. So you have 2 to the 15x equals 2 to the 6x minus 2. The common mistake there is I'll see students frequently just write that. And so you have to be really careful here. I'll see students frequently write that as 2 to the 6x minus 1 power. Right? They'll fail to use the distributive property to multiply that out. So you got to watch for that. And now what do we got here? We've got that the bases are the same right here, right? Bases are the same. That's what we're trying to do. And so when the bases are the same, what has to be true? The exponents have to be the same also. That's the only way that statement can be true. Exponents must be the same. And so let me write that here. We're just using that rule that we've been using on these last couple of problems. Exponents must be equal. And now I've got a simple equation to solve for x. I just subtract 6x. I get 9x equals negative 2, or x equals negative 2/9. Excuse me. And so that would be the solution to this equation, negative 2/9. All right. Okay, let's look at another problem. Say I have a couple more examples I definitely want to work here. Let's say I have 1 over 5 equals 25 to the 4x minus 2. All right, so you got a 5 and a 25 in there, so you're kind of thinking powers of 5 here on a problem like this. Powers of 5. But you have to be careful that 1/5, if you're going to write that as a power of 5, that's a fraction, and so you have to use negative exponents there. That 1/5 is really 5 to the negative 1 power. Remember that negative exponent takes the number, doesn't make it negative, remember, it flips it, right? Changes it into a fraction. So 1 over 5 is really 5 to the negative 1. And then 25 is really 5 to the second. Right, and so now you're starting to head towards everything being a power of 5 here. All right, and so remember what we talked about in the last problem. You have to multiply exponents on the right side here. So multiply exponents. And you have to use the distributive property on that right side there to multiply those. So you have 5 to the negative 1 equals 5 to the 8x minus 4 power. And so now all of a sudden the bases are the same. Bases are the same. They're equal. That's your goal here with this type of exponential equation. And so what has to be true here? The exponents have to be the same also. So you have that negative 1 has to be equal to 8x minus 4. And then solve that equation for x. You're going to usually end up with a simple equation here to solve. If I just add 4, I get 3 equals 8x. Divide by 8, I get x is 3/8. And that's my solution to this equation is 3/8. That's the x value that's going to make that equation a true statement. 3/8. All right, let's see. So next problem I want to look at. So by the way, this next problem is actually out of your textbook, section 6.6, page 535 of your book. And this is problem number 6. I think I'm going to work 2 more problems, this one and another one, out of your textbook here, and then that will be it. So this one is 3 to the 2x plus 1 times 3 to the x equals 243. All right, so the bases here on this problem are 3's and this 243, but all of those numbers are powers of 3. 243 is a power of 3 also, by the way. It is 3 to the 5th power. Now, I'm not going to give you one, if I test you, I'm not going to give you one where it's that bad, that's that big of a number. So it's going to be a little bit more obvious than 243 was. Now, on the left side, you've got bases multiplied together. So what do you do there? Remember, there you add exponents. So on this side of the equation, you're going to have to add exponents. So this is 3 to the 2x plus 1 plus x power, because you're adding the exponents there, equals, and then 243 we've already identified as 3 to the 5th power. And so on the right side, this is 3 to the 3x plus 1 equals 3 to the 5th. And now the bases are the same, right? That's what you're trying to get to, remember. Bases are the same. And so the only way that that statement can be true is if the exponents are also equal. So you get 3x plus 1 equals 5. Subtract 1, you get 3x is equal to 4. And then divide by 3, and you get x equals 4/3. You know, once you get the bases to be the same, these have been typically easy problems, but sometimes getting those bases to be the same can be tricky. So, and we've seen now a variety of different situations that come up here. So, all right, let's look at, to finish this, let's look at problem number 10. And this will be our last problem here. So you have, let's see, this is section 6.6, page 535 of your book. And this is number 10. And this is a messy problem. You have 1 over 64, all raised to the 3n power, times 8 equals 2 to the 6th power. So this is kind of yucky here. And the 64, the 8, and the 2 are all powers of 2. You know, 64 is 2 to the 6th power. 8 is 2 to the 3rd power. And, you know, you've got the 2 on the right side of the equation already. All right, so let's see what we've got here. This 1 over 64 then is 1 over 2 to the 6th power to the 3n. Times 8, which is 2 to the 3rd power. And this is 2 to the 6th. And then 1 over 2 to the 6th, don't forget, we've talked about this, you have to use negative exponents in a fraction like that. So 1 over 2 to the 6th is really 2 to the negative 6 to the 3n, times 2 to the 3rd equals 2 to the 6th. So then you have 2 to the negative 6 to the 3n is really 2 to the negative 18n. You have to multiply those exponents. Times 2 to the 3rd equals 2 to the 6th. And then you're multiplying bases there, so this is going to be a place where you add the exponents. You have negative 18n plus 3 is the exponent there, equals 2 to the 6th. Wow, so let's see. So going back in and putting a few notes in here, you had to multiply exponents here. because you had a power raised to a power. So you had to multiply those exponents right there. You had to use negative exponents on the step before because you had a fraction there. You had the power in the denominator. So you had to use negative exponents on that fraction right in there. And then finally, you had to add exponents right here. So you have to be pretty good at rules of exponents and know when to add or to subtract or to use negative exponents, things like that. All right, and so then finally, what have we got? Bases are the same. In that step right there. And so finally, when we get to that point, we get that the exponents have to be equal. And that's the easy part of the problem. The hard part was the part above it, certainly. So you have negative 18n equals 3. And so n is negative 3 over 18, or negative 1/6. And that is my solution, negative 1/6 right there. All right, now at this point, if you've been following along, and I know, I've worked through quite a few examples here, and if you've been following along on these last problems, notice every one of them, I could write the basis so that they are the same. So on this problem, I ended up with 2 to a power equals 2 to a power in the equation, right? Let's see. On the problems previous, on this problem, I ended up with 5 to a power equals 5 to a power. On this problem, I ended up with 3 to a power equals 3 to a power. Right? Going back through all of these, ended up with 2 to a power equals 2 to a power. 6 to a power equals 6 to a power. So notice that as we work through all of these problems, 5 to a power equals 5 to a power. The bases ended up being the same on both sides of the equation. And the question is, can I always do this? And the answer is absolutely, totally no way, right? That doesn't always work. This method does not always work. I guess that's probably basically the way to say it. Does not always work. Just looking at a very simple equation like this, if you had 2 to the x equals 5. It's a super simple equation, but notice that the bases cannot be written as the same number. You have a 2 and a 5 as the bases. Bases cannot be written as the same number. Even though it's a super simple equation, this is actually somewhat more difficult to solve than the previous problems. We must use logarithms to solve this type of equation. And this is our topic for our beginning topic for Wednesday. We use logs to solve this type of equation. And that's our topic for Wednesday. So on Wednesday, what we're going to do is we're going to do exponential equations part 2, where we have to use logarithms, and then we are going to start in on log equations. And with log equations, I kind of break those types up into what I call type 1 and type 2 log equations. And so I will do type 1 on Wednesday. And then next Monday, I will do log equations type 2. And you don't know what type 1 and type 2 log equations are yet. Don't worry about that at this point. And I'll also look at compound interest there on Monday as well. Or I might actually look at compound interest on Wednesday. So somewhere in there, we'll be looking at compound interest problems and looking at an application or two there. All right, so if you're looking for practice On section 6.6, on exponential equations, just a few problems there. This is page 535, problems 5, 7, and 9. And then section 6.5, these are problems on practicing the properties of logarithms, contracting and expanding, and the change of base formula. This is page 525. There, you're talking about problems 1 through 23. Would be great practice problems, really good practice problems. And actually, now that I look at it, problems 25 and 27 would be change of base problems. Actually, I'd say 33 and 35. Yeah, that would be better. 33 and 35 and 37 for change of base problems. So those would be good practice problems there out of the textbook if you're looking for more practice. Plenty of practice, by the way, on your review for these.